What's up, people? How's it going? Welcome back to CP with Sundar. Now, in this segment, we'll be discussing about how to do updations and then queries on the segment tree. So, in the previous video, we discussed about how to build a segment tree using the arrays. So, if you haven't watched that video, I recommend you to watch it before this so that it will be easy for you to understand the updation and then the querying part. Right? Without any further ado, let's get started with the updation. Now, when we talk about updation, we can do point-wise updation and we can do a range-based updation. So, point-wise is nothing but we'll be updating only one of the elements, and in the range-based we'll be taking a particular range and then we'll be updating all the values in that particular range. Now, let's start with the point-wise updation. For point-wise updation, we just need to modify one of the elements. Let's say we want to update the second index by 2. That is, we want to increment the value of second by 2. So let me just put it in this way, right? So what we can do is we can just go to that particular element over here. So the second index will be 5 in this particular example. So we are taking the array as 2, 3, 5, 7, 4 and 5. So the second element will be 5. So we can just go to that particular element and we can increment it by 2. So similar to the building of the segment tree, we'll be just partition the array, and whenever we get to one of the leaf nodes which is matching, then we'll be just updating it. Code will be just similar to this building, but except the base case. So inside the base case, whenever s is equals to e, then we'll be just updating that particular index by the value that is going to be incremented. And then we'll also update the actual value inside the array. So the index will be yes, and then we'll be incrementing it by incr variable, right? So this will be the point-wise updation. So we just get that particular leaf node and then we update it. So when can we say that a node is a leaf node? Whenever the indexes are same, then it's a leaf node, or it will be having an array which has only one element. So this is in regards with the point updation. Now let's get to the second part, which is range updation. So whenever we get segment tree problems, we'll always be given with some range updations, right? So that's the hot topic over here. Now let's say we want to update the elements in the range of 2 to 4. And all we want to do is increment it by 2, right? Now, how can we achieve this? So let's get to the segment tree which we constructed in the first part, right? So this is a segment tree that we have. Now, where are the elements? So this is the first element, or the 0th index, first index, second index, third, fourth, and then 5. This corresponds to the given array, right? So if you want to modify the values of 2 to 5 or 2 to the range 4, then we have to modify the elements, this 5 and these two elements, 7 and then 4. But if you notice over here, this 5 is in the left subtree and then 7 and 5 is in the right subtree to the root node, right? So how can we get to these different leaf nodes and then modify them? In the name method, we would have just laid out a loop in the range of loop which goes from 2 to 4, and we'll be modifying the array, right? So similar to that, we'll be having one linear solution for it, and then we can also do this in logarithmic time. So in the linear time, we'll be just going to all the leaf nodes and we'll be modifying it. So it's similar to point-wise updation. We'll be going to all the leaf nodes and we'll be updating it. So how to get to all the leaf nodes in the first place, right? So if we start from here, we'll be having some L and R. That is, 2 is L and then R is 4. So left and then right. So these are the ranges, right? So I have to modify all the elements within this range. Now if you see this particular subarray, so the starting index is 0, ending index is 2. Now for this subarray of 7, 4 and 5, the starting is 3 and ending is 5. So we'll be just playing with the starting index, ending index, and then this L and then R, right? Now let me just try to lay out some number line and then plot these variables. So let's say this is the number line that I have, and then let's say our L starts here and then it goes till this point, right? Now let's say the subarray starts here with S and then it's ends with E. Now if you see over here, the subarray is not even overlapping with the given range, which means that there is no updation that is required for any of these elements that lie in this particular range, right? So we'll be just skipping the updation for the range of S and E, right? So there could also be another case like S starting here and then E ending here. So even in this case, it will be outside the range of L and R. So we'll be just skipping it. So how to formulate this in code? So we can just say that we can just write this as a base case. So if the value of E is less than L, or the value of S is already greater than the value of R, then we can just return back, because there is no requirement of any of the updations, as it doesn't lie within the ranges. Now, the updation is only possible when some segment of S and E overlaps the range of L and R. That is, the number line will look something like this. So we have the number line, and we have the range just L and then R. So the overlapping could be complete overlapping or some partial overlapping. So in the case of S being here and then E being here, we'll be having a partial overlapping. That is, only these segments will be needing the updation. Right now, we could have another case like another subarray starting here. So let's say this is S1 and then it's ending over here. This is E1. So the entire subarray is gonna be updated, right? So this is complete overlapping, and this case is partially overlapping, right? So in both of these cases, there is be it any partial overlapping or complete overlapping, we just need to dive deep into that particular subarray, and we have to dive deep till we arrive at the leaf nodes. And when we arrive at the leaf nodes, we'll be updating the those values, right? So we can be implementing it similar to the building of the tree. The rest will be just dividing the subarray into two parts. Now we'll be having a left subtree and a right subtree. So we'll be just looking at the ranges of it. That is S and then E. So if it goes completely outside of the ranges, then I'll just return back from the invoking function, right? Otherwise, I'll be trying to dive deep into it, and then I'll be going till the base case is achieved. That is, till we get to one of the leaf nodes, and I'll be updating it, right? So this is how we can do the updation in linear time. Now let's try to implement this. Now let's continue from where we left in the previous video. Now our task is to do updates on a range, right? So let me just name this as update range, and then the parameters that we need are index SE, which is similar to the build tree, right? So it will be index S and then E, and in addition to that, we'll be having the range which we want to update, that is L and R, and then let's just pass the vector, right? So as we discussed over here, so the first base condition will be to check whether that particular subarray's range is overlapping with the range of L and R. Then there will be no overlapping, so we'll be just returning from the function. Otherwise, we'll be just trying to break the array in two parts, and then we'll be going till the leaf node is reached, right? So let's take out the middle value, which is S plus E by 2, and then we'll be just invoking this update range function with the children's node, right? So it will be 2 times of index, and then it will be going from S to mid, and the L and R will be just the same thing, right? So this will be the case for the left subtree, and then the right subtree will be 2 index plus 1, 2 times of index plus 1, and then the ranges will be mid plus 1 till E, and L and R and array will be passed, right? So this should be done till the leaf node is achieved, right? So the other base case will be whenever we go to the leaf node, we'll be updating the tree of index by the value which is going to be incremented. So let's say we also pass the value which we have to increment to, right? Also we can just update the value in the actual array by the increment value, and we can return over here, right? So we have modified the leaf node. Now for all the intermediate nodes, I'll be just doing the same thing which we did go here. That is, for the intermediate nodes, it will be the sum of its children. So that's it. So this is how we can construct the update function in linear time. So why am I saying this as linear? So the time complexity will be linear because we're going to all the leaf nodes that are within the range L and R, and then we're modifying it. So it's just similar to the naive approach, right? So the naive approach, we have laid out a loop which goes from L to R, and then we have modified the actual array. It's just similar to that. We're going to all the leaf nodes and we are modifying it. So even this time complexity will be big of n. We have an approach called lazy propagation, where we can achieve the same thing in logarithmic time. But we can discuss that after discussing the method of querying. So let's first discuss how to do a basic querying, and after that we can jump to the logarithmic way of updating and then querying. Right, now let's see how we can query over the given segment tree. Let's discuss the querying. The way in which we can query is just similar to the way in which we update it. So let's say we want to get the sum of the values in the range of 2 to 5. So if we say 2 to 5, then 2 is here, and then I'll be getting all the values in the right subtree, because right subtree goes from the indices 3 to 5, right? So I need the whole right subtree and then one part of the left subtree, right? So how can we do that? So even this can be done in the way which we discussed for the updation. So for the updation, we'll be first looking out for the range, right? So whether the S and E lies within the range of L and R, or does it have any overlapping with the L and R? So if it doesn't have any overlapping, then we can just return it, right? Now if it has some overlapping, then we'll be first checking whether it's a complete overlapping or incomplete overlapping, that is partial. So if it's completely overlapping, in this case, if you see, this 3 to 5 is completely overlapping. So there's no point in diving deep. We can just return this particular sum which we have, right? So we can just return 16 from here without diving deep. So if we dive deep, then we are wasting time. So if S and E completely lies within the range of L and R, then we can directly return the value which lies at that particular index. So if it has some partial overlapping, then we'll be trying to break that array into two parts, and we'll be doing the steps which is similar to updation part. Right? So if it doesn't lie within this range, then I'll be returning back. So this is for the queries, right? So the first base case will be if the ending of the first subarray is lesser than the starting of the range, or the starting itself is greater than R, then we'll be returning back, because we don't need anything from that particular subarray. Now we will be having two cases. One will be complete overlapping. Now, when is something said to be complete overlapping? If S and E lies completely within the range of L and R, which means that L should be in starting position, and then the S should be followed by that. After that, E should come, and then R should come. That is, if you lay these elements in the timeline, it should be something like this. We have S in the L in the first place, and then followed by S, followed by E, and then followed by R. Right? So only then we can say that this S and E is completely overlapping in the range of L and R. Right? So that's what I have written over here. If S is greater than or equals to L, and then if E is less than or equals to R, then this is a case of complete overlapping. Now in this case of complete overlapping, I do not go to the I do not dive deep and then waste my time. I can just return the value which is present at this particular index. Right? So this is in regards with the complete overlapping. Now we'll be having a case which is incomplete overlapping. So for incomplete overlapping, we don't have any other method. We just need to divide the elements into two parts, and we'll be diving deep into it, which is similar to this particular code which I have written over here. And after that, we'll be constructing the solution for the intermediate elements. If you see over here, I am returning the values of tree index. So if it doesn't lie within the range, then I can return the value of 0, so that it doesn't affect my answer, right? So I'll be calling the left subtree. The returning value of the left subtree can be stored in, let's say, a variable left, and then this is the answer for the right subtree. I'll be just returning back left plus right as such. Right, after getting the left and right sums from the subsequent calls, I can just return back the sum of left and right. So this is how we can implement the query. Right, now let's try to implement this. Now we want to query over the given segment tree. So let me name the function as query range, because it's a range based query. Right, so the parameters will be index S and then E, and we'll be getting a range in which we have to query, and then we can just pass the array if you want to, but we will not pass the array because it won't be used anyway, but let's just pass it as it is. Right, now what are the base cases which we have? We'll be having the first base cases the same thing which we did for update range, right? So this is for no overlapping. Now if you have complete overlapping, that is, if L is less than or equals to S, and then E is less than or equals to R, then it's complete overlapping, right? So let me just name it as complete overlapping. Now in this case, we will be just returning back tree of index. So as we are returning back an integer value, the return type will be int, and then when there is no overlapping, I can just return back 0 so that it doesn't affect the actual sum which we return. Otherwise, we'll be just dividing into two parts, and we can calculate the mid value as s plus e by 2. We'll be having the index as 2 times of index s comma mid, and then l comma r, and then we can pass the array, and then right subtree will be having the index as 2 times of index plus 1, and then the starting index will be mid plus 1, and then the ending will be e, right? So this will be the two functions which we could have, or two partitions. Now for each of these partitions we'll be getting a return value. So let's say this is the left sum, and then this could be the right sum. Now we'll be just returning back the sum of left sum and then right sum. Okay, so this is how we can implement querying inside a given range of L and then R. Now let's verify whether it's working correctly or not. I have built the segment tree. Now let's try to execute this. So let's give the same array as the input. So the elements are 2, 3, 5, 7, 4, and 5. So this is the segment tree that we have. Now let's try to query the answer for 0 to 2. So for the 0 to 2, the sum is 10, right? So let's just verify it. So the 0 to 2 will be 2 plus 3 plus 5, which is 10. Yeah. Now let's try to get the sum in the range of 3 to 4. So 3 to 4 will be having the elements as 7 and 4. Hence the answer will be 11. Right. So this is how we can build both update range and then query range functions. So for update range, it's nothing but we'll be first checking whether the given subarray has some overlappings. So otherwise, if you get the leaf node, we'll be modifying or we'll be updating those values. Now, as far as query is concerned, the same logic applies here. So if it doesn't have any overlapping, just return 0. Otherwise, if it's completely overlapping, then we'll be returning back the element which is stored at the particular index. Otherwise, in the case of partial overlapping, we'll try to divide the elements into two parts, and then we'll be diving deep till one of these two cases are satisfied. So that's how we can do updation and then querying. Now, as far as updation is concerned, so updation will be running in logarithmic time because we're just going to the first value wherever it is matching. So if it's completely matching, we don't waste the time. Rather, we will just return back the function. So that's why we won't be going to all the leaf nodes, but we'll be just returning back whenever some range is completely within the given function. Hence, the querying will be having a logarithmic time. And as far as this update function is concerned, it will be having a linear time, but we can improve the time complexity using a method called lazy propagation, which I'll be discussing in the next video. So that's all for this video, guys. I really hope that you enjoy the video and learn something about the segment trees. And all the videos that I make about segment trees will be added in the playlist of segment trees and range-based queries. And if you haven't subscribed to this channel previously, please do subscribe so that you get the latest notifications. And that's all about it. So have a great day, and until next time, it's me soon signing off. Goodbye.